So sickle cell, it's a chronic disease that causes the oxygen in hemoglobin to just kind of deplete. So it's a very painful disease. It causes people to have organ failure and a shorter lifespan. More specifically, people with sickle cell averagely don't live beyond 48 years. So this is me and my brother, and my brother's actually a carrier for this gene. So meaning that let's say you were to get married and have a kid, they would probably be likely to have the sickle cell trait. So what is sickle cell anemia? So usually our red blood cells kind of look like a coin, they're like circular, but when the red blood cells, when there's a mutation in the hemoglobin beta gene, this is what the sickle cell, like red blood cell, kind of looks like. It's almost like a crescent moon shape. And this is because deoxygenation, so it compromises the shape and the function, and oftentimes these little sickle cells are sticky. And inside the blood vessels, they stick together, and this makes it hard for the blood to flow throughout the veins, and just kind of causes organ failure and damage because the blood and oxygen can't get through the tissues and just flow. So what is pyruvate kinase? So this is kind of the textbook definition of it, but pyruvate kinase is really just a part of glycolysis. But more specifically, what does it do for the red blood cells? So pyruvate kinase actually increases the affinity of oxygen to red blood cells. So how does it do this? It does this by increasing ATP, which we know is the energy source for all cells, and then by decreasing DPG, which is kind of the red blood cells' affinity to oxygen. So by increasing ATP, we increase the integrity and energy of the cell, making the cell a lot more durable and stronger. And by decreasing DPG, this kind of prevents the cell from giving more oxygen to tissues and stuff like that, which is kind of what we want in these sickle cells, because we want to keep as much oxygen as we can instead of releasing the oxygen that the cells frankly don't have. So the mice that we're using in today's experiment, so these are Towns and Berkeley mice. So the difference between these mice, they're really just both used for testing, like blood testing, especially in human trials. But for Towns mice, the mouse hemoglobin beta genes are completely deleted. So instead of partially inserting the human genes, the human genes are just randomly inserted. So this makes the mice have a shorter lifespans, more severe anemia, and just less controllable. So for the Berkeley mice, we partially replace the genes, and this kind of makes it a longer lifespan, mild anemia, and we just place the human genes right in the same place that the mouse hemoglobin genes were. So these are the baseline tests. So by doing this, they kind of took the blood of all of the mice, and these are the tests that we got from all of these mice. So on the x-axis, we have all of the types of mice. We have the wild type, which is just normal mice. We have the Towns HBAA, which is non-sickling mice, HBSS, the sickling mice. We have the Berkeley non-sickling, and then the Berkeley sickling. And then on the y-axis, we have hemoglobin, which is just the amount of hemoglobin in the red blood cells. We have the red blood cell count, the amount of blood cells. We have the hemocrit, which is kind of like the ratio, and then we have the MCV, which is kind of just like the size of the blood cells. We have the MCHC, which is just the concentration, and then the reticulocytes, which is just the amount of immature cells in the testing. So for hemoglobin, we kind of see that there's less hemoglobin in the sickle cell mice than the HBAA in both cases. In the reticulocytes, we can see a heavy increase from 4.1 to 42.7, and then 6.2 to 30.4. So this is kind of like normal in people that have sickle cell, because their body kind of wants to compensate for not having the healthy blood cells. And then the MCV, this is also increased because the size of reticulocytes are typically bigger than the size of normal blood cells. So So keep this in mind when we talk about the compound A and kind of how it affects all of these factors. So this is the first test. So this is a test on PK activity using compound A. So on the y-axis we have the PK activity, and then on the x-axis we have all the types of mice. So on the left we have PEP 0.5. So what does that mean? PEP is kind of used to make PK in glycolysis. So they tested these at different levels kind of to see how compound A affects the affinity of PK and PEP and like the relationship between them. So in the first chart, we see that Berkeley S mice, the PK activity increases by 0.03, and then the rest is non-significant. So this is kind of interesting because Berkeley mice, it's kind of easier for them to see like a stride in this testing because they have less severe symptoms, and it's like they don't have the random gene kind of like the Towns AA, so it's harder to see a result in Towns AA. But this does show that they are kind of making an improvement in PK activity with Berkeley sickling mice and non-severe sickling. So then we have the PK-PEP 0.2. So this is a lower PEP level. And strangely enough, the compound A actually works better when at a lower level, where we can see in the Berkeley cell, it increases by 0.004. So this means that the compound A increases the affinity to PEP, and this is kind of interesting because even with low PEP, PK activity can still die. And then in the next chart, we see that hexokinase activity isn't affected at all, so compound A only affects PK activity and not any other activity.
Sorry, Jordyn, you kind of said this, but what does compound A bind to? Is it PK?
Okay, so point of sickling. So this is kind of determined by the oxygen gradient or the Lorca analyzer. So they kind of determined the elongation index, and if the elongation index goes under 5% of the maximum of the blood cells, then they call this point of sickling. So on the x-axis we have all the mice, and then on the y-axis we have point of sickling. So in the wild type there's no sickling. Towns AA, no sickling, and then Towns SS, there is some sickling, but even with compound A you can kind of see a decrease in sickling, which is interesting because even Town SS, it's the hardest to see results. So yeah. Okay, and then metabolic levels. So this is kind of what I was talking before about how we wanted to see an increase in ATP and a decrease in DPG. So in the wild type, in all the DPG, we see all significant factors except in the Berkeley non-sickling, which is a really good stride. And we have an increase or a decrease in all of them. And then in ATP, we actually don't have a significant stride unless in Berkeley non-sickling, which isn't kind of like the factor that we want to target. But this is a great start to kind of increasing ATP while decreasing DPG at the same time. Okay, so now my conclusion. So in conclusion, sickle cell, it's a horrendous disease that kills many and causes a lifelong pain for many people. And this kind of stride with PK activity and trying to increase it is a good start to kind of curing this now incurable disease.
Can you go back a slide?
Yeah.
Or one more. For this one, why is there not a significant difference in the Berkeley sickling mice despite having the compound A and everyone's in the towns?
I'm not sure. Actually, it would actually make sense for it to have more of an impact in Berkeley S, considering that the Berkeley S has less severe symptoms, but I guess it just affects Town S.
Sure.
Jefferson, I have a question about compound A. I came in a little bit later. Could you describe a little bit more what the chemical makeup of compound A is?
It's kind of just something to like activate PK. The journal really didn't describe like kind of what compound A really was. It just kind of like described like the target of what it wanted to do and kind of how it wanted to help people.
So it activates?
Mm-hmm.
Okay.
Thank you.
Wait, so could you explain again like how sickle cells like reduce pyruvate kinase activity?
How sickle cell reduces it?
Like do people with sickle cell disease have like lower pyruvate kinase activity?
Normally, yes, but sometimes they do have normal levels, but even the normal levels that they have isn't enough to kind of help the sickle cell.
Can you just re-explain like what pyruvate kinase like does?
Okay, so mainly it's for glycolysis, so this is kind of like the production of glucose, and PEP is kind of like in this like, it's kind of in this too, but it's really just like an enzyme that just like catalyzes the conversion of PEP to pyruvate. Yeah, so it's just like to make glucose, but it's also kind of activating all the cells, the blood cells too. And you can kind of use it to kind of increase the ATP. Are there any more questions?
Just still, again, I also, my bad, but, pyruvate kinase is the expression of pyruvate kinase lower in sickle cells? Like there's less of the enzyme, or it's just not as active, or are you just trying to target pyruvate kinase because it's a glycolytic enzyme, so you're trying to just increase?
I think we kind of target it because of the ties to both ATP and DPG, but